Okay, our next one here, so we just did ketones. We're going to look at, there's one slide here that says ketones with tautomerization. Skip that for the moment because we don't know what the tautomerization is right now. We'll learn that in organic too. Aldehydes is next. So what do we see with an aldehyde? Aldehyde also has the carbonyl. Here's the general formula for an aldehyde. So it has a C double bond O stretch as well. Just like the ketone did. Maybe just a little bit different in where it comes, but it's still pretty close to about the same place. It's about 1690 to 1740 reciprocal centimeters. And again, very, very strong. It's going to be, carbonyl is always, almost always, 95% of the time, it's the strongest peak in the spectrum. Easy to pick it out. The other thing that an aldehyde has, that the ketone doesn't, is we can see the aldehyde CH stretch. So from the aldehyde, it's got that CH of an aldehyde. I'm going to call it an aldehyde CH stretch. And that is about 2830 down to about 2700 reciprocal centimeters. I've been starting with the lower number. Let me change that. It's the same. I'm just going to put the big lower number first here. So 2700 to 2830. Now let's look at an example of that and see if we can pick those out. So we should be able to see the CH stretch of the aldehyde and the carbonyl stretch. Again, I like to go 3000 first. Right below 3000, sp3 CH stretching. That's from the alkane portion down here. All these CH2s and CH3s. That's giving those peaks right below 3000. The CH of the aldehyde, that's even lower than the sp3 CH stretching. That's this 1715 is the aldehyde CH stretch. Is that 1715 right there. So we had said 1700 to 2830. That's the CH of the aldehyde. So it's going to stand out. It's below any of the sp3 CH stretching here. It's going to stand out. The 1728, that's our carbonyl. That's the C double bond O stretch. And typically it's normally the strongest peak in the spectrum. This one here is one of the rare examples. It's not quite the biggest one, but it's still really big. Still really strong. I don't know why it's not the strongest. Normally it's the strongest. Like I said, about 95% of the time it will be the strongest. Everything else is 1500 below fingerprint. We're not of concern to us. This one also has a little bit of OH in there. So that could be water, or it could be a little alcohol that's in there. Some little impurity that's in there. So when we start taking IR spectra of your products in the lab, I will be able to see impurity peaks. You got peaks to identify your product, but then you also have impurity peaks as well. So I will be grading you on that. Okay, so that's an aldehyde. Questions on aldehydes? We're next going to look at a carboxylic acid. And a carboxylic acid is extremely easy to identify. There is nothing that looks like a carboxylic acid. Carboxylic acid is going to have a carbonyl. So we will have a C double bond O stretch. And it will come at about 1710 to 1780 reciprocal centimeters. And again, very strong. Normally the strongest peak in the spectrum. The other thing that a carboxylic acid has is an OH stretch. The OH stretch of a carboxylic acid is about 2,500 to 3,000 reciprocal centimeters. Now, if you look back in your notes, we talked about the alcohol. Alcohol has an OH stretch. And we said the alcohol was about 3,200 to about 3,550 reciprocal centimeters. So the carboxylic acid OH stretch is a lot lower than the alcohol OH stretch. Why? What is different about a carboxylic acid? Let's put up the general formula for a carboxylic acid. So why is that OH so much lower than an alcohol OH stretch? Resonance. That OH has resonance into the carbonyl. Resonance lowers your frequency. We've talked about that. So it's a lot lower than an alcohol OH because the carboxylic OH has the resonance with the carbonyl. Now the other thing that I'm going to write up for our OH stretch, it's easy to pick out. It is going to be very, very broad. OH hydrogen bond, OHs can hydrogen bond, but a carboxylic acid OH has stronger hydrogen bonding because it can hydrogen bond to the carbonyl, so you get two carboxylic acids always come together and dimerize. Let me show how that works. They always come together and dimerize, so two of them come together and we get hydrogen bonding here. So you get hydrogen bonding to the carbonyl, that hydrogen bond, and this one will do it to the other carbonyl. So the hydrogen bonding in carboxylic acids is much, much stronger than it is in an alcohol. So that makes it even broader. I mean, it's extremely broad. And I'm also going to write up my little niece. She would fuss at me for this. She says this is a bad word. It's ugly. It's very, very broad and ugly. She doesn't like it when people use the word ugly. But it's very broad and very ugly. And I'm going to show you why I call it ugly. Let's take a look at a picture of a carboxylic acid. First of all, we're going to pick out the carbonyl, C double bond O. That's that 1717. That's our C double bond O stretch. Again, strongest peak in the spectrum. Almost always, like I said, 95% of the time you have a carbonyl, it's going to be the strongest peak in the spectrum. We did mention the 3000. I always love 3000. We've got peaks right below 3000. That's our SP3 CH stretching. That's from the alkyne portion. Our OH stretch, this is the OH stretch. This entire thing here is the OH stretch. That OH stretch is right here. Now, it is overlapping with the SP3 CH stretching. And that's why I call it ugly. It's not a nice, pretty, smooth curve like we saw with the alcohol back here earlier. There was the alcohol. See how pretty and smooth that is? I call that pretty. This is pretty and smooth, broad and pretty and smooth. But we look at the carboxylic acid, extremely broad. This is the OH here of the carboxylic acid. And it's jaggedy and ugly. It's not that pretty smooth curve because it's overlapping with the CH stretching that we've got there. sp3 CH stretching in this case. But carboxylic acids, there's nothing else that's going to look like carboxylic acid. You're going to have that big, broad mess down here that's ugly, and you got a carbonyl. You got to have both of them to be a carboxylic acid. So alcohols are extremely easy to pick out, and carboxylic acids are extremely easy to pick out. Those are the easiest ones that we've got. Questions on that? We're next going to look at esters. Ester has a carbonyl, but you're not going to be able to pick out. Nothing about an ester really stands out different than, say, a ketone. The ester does have a carbonyl, so we'll see a C double bond O stretch, and it's in the normal range of most other C double bond O's. The C double bond O, the carbonyl, that's the 1771 right there. That's our carbonyl stretch. Let's see what else we got. Here at 3000, we got some peaks right above 3000. That's sp2 CH stretching from the phenyl ring. We do have an sp3. That might be that little tiny one on the side there. It's showing up small for some reason. And what else we got? 1601. 1601 is a C double bond C stretch. That's from the phenyl ring. That's the carbon-carbon double bond stretches. And they're lower than normal because of the resonance. And everything else is 1500 below fingerprint region. We're not of concern to us. So there's really nothing any different with the ester here than if we had a ketone. You're not going to really be able to pick the difference between them. Let's see, what did I have for the ketone back here? Yeah, look at the ketone. Ketone, we had the phenyl ring, so you had same things. You had the C double bond C and the sp2 CH stretching, and then we had the carbonyl. And then you look at the ester and it looks almost the same. Maybe a slightly different spot, but everything else is exactly the same. There's the C double bond C, exact same place on the C double bond C. Basically the same place on the sp2 CH stretching. So nothing really stands out. Unfortunately, that carbon-oxygen single bond is down in the fingerprint region. They're often difficult to pick out. This one's not too hard. It's coming right here at 1200, but most time they're difficult to pick out. So I'm not going to ask you to go find those. So I will not have you pick between an ester and a ketone. I will not have you identify the difference in those. They basically look the same. We're next going to look at amides, or amides, however you want to pronounce. And we're going to look at the difference here in some classification of those, primary and secondary. There are some things that we can pick out on these. So let me write some things up here. With the amide, we have an NH stretch. If the nitrogen has a hydrogen on it. You wouldn't have to. If you had a tertiary amide, wouldn't have a hydrogen. But if we have a hydrogen, we'll have an NH stretch. And that curves 3100 to 3450. And they're normally medium in intensity, so I'll put an M out there for medium. The cool thing is I can tell the difference between a primary and a secondary amide. If you have the secondary amide, you only have one hydrogen on the nitrogen, and we get one peak. If you have a primary amide, you have two hydrogens on the nitrogen, and we get to see both of them. We'll see two peaks. Primary amides show two NH stretches. Secondary only shows one NH stretch, and tertiary doesn't show any NH stretch because it doesn't have a hydrogen on the nitrogen. So we can tell the difference in those. The other thing that the amide has, of course, is a carbonyl, so we will see the C double bond O stretch, and that's in the normal range of most carbonyls, maybe a little bit on the lower side, about 1630 to 1690 reciprocal centimeters, and of course always strong in intensity. All carbonyls are strong. So let's look at some examples here of the amides. First one I have is a primary amide. So we do have the carbonyl, the C double bond O. That's this one here at about 16, 17, 18, okay, about 1640 or 50 right there. That's our C double bond O. 3000, I forgot to mention that, 3000. We got some peaks right below 3000. That's sp3 CH stretching. That's from the alkane portion there. But up here, we have the NH stretching. And we get to see two of them because it's a primary amide. You have two hydrogens on the nitrogen. You get to see both of those NH stretches there. Now you notice those peaks, those NH stretches there, they are in about the same place as the OH of an alcohol. They are also in about the same place as the SP CH stretch of the alkyne. All of them are coming at about the same place. Now we already talked about the difference between the alkyne CH and an OH. Alkyne had no hydrogen bonding, so very, very narrow peak. OH had hydrogen bonding, very, very broad. NH stretching, NHs also can hydrogen bond, but they're not as strong as an OH. So they're broadened a little bit, but not as broad as an OH. So although they come at the same place, you can tell the difference in them. You can see these are a little bit broad, but nothing like the alcohol that we had back earlier. You look at the alcohol, look how broad that is. It's, even though they're coming at this about the same place, it's no problem to tell the difference between an NH and an OH. And then we can also still tell the difference with the alkyne. Look how narrow that alkyne is. It's a very narrow peak because it can't hydrogen bond. So although all three of them come at the same place, basically, you can tell the difference in them based on the broadness of the peak. Very narrow, it's an alkyne CH. A little bit of broadening, it's an NH. A lot of broadening, it's an OH. Questions on that? Everything else here was 1500 and below, fingerprint, not of concern. Here is a, you're going to look next at a primary amine. And we just went through the amides. Amines also have NHs. So if we look at the amine, instead of the amide, the amine shows an NH stretch at basically the same place. So 3,300 to 3,500 reciprocal centimeters. Typically medium in intensity. And if you have a primary amine, that will show 2 NH stretches. Just like we saw with the amide. So that part's the same. Of course, the amine doesn't have the carbonyl like the amide does, so we don't get to see that C double bond O, so you can tell the difference in them. So let's look at an example here of a primary amine. So with this one, love go to 3000 first, right below 3000, sp3 CH stretching, that's all the alkane portion. Here at 3200, 3372, those are our NH stretches. We have 2 of them, so that's telling us that it's a primary amine. You've got 2 hydrogens on the nitrogen. Most everything is 1500 and below, fingerprint region. There is something here right at 1600. I have no idea what that is. That's some kind of impurity peak. It doesn't belong there in the spectrum. I don't know what would be in there. Maybe they had some, maybe they didn't clean their glassware, let it dry out. There might be some acetone still in there or something. That's in the range of a carbonyl, and there's no carbonyl. Now, I know it's an impurity because it's not a really big peak. It doesn't belong to this because it's not a big peak. If that had been a real carbonyl and it belonged to this, it should have been the biggest peak in the spectrum. So I know that's just some impurity peak. So if we look back at the carbonyl, like with our amide here, see the carbonyl is the biggest peak in the spectrum. Here it's not. It's probably what it is. It's probably a little bit of amide in there. One way you can make amines is from the amide. You can reduce an amide to make an amine. So maybe they didn't fully reduce it. So there's still a little amide in there. So we still get to see some carbonyl. Their reaction just didn't go to completion. They didn't let it react long enough. So that's probably what's going on. I also have a spectrum of a secondary amine. So the secondary amine, you're only going to see one NH stretch. And here is our NH stretch from the secondary amine, here at 3292. Other things we have, we've got peaks below 3000, that's sp3 CH stretching, that's from the alkane portion. Everything else is 1500 and below, not a concern to us. Fingerprint region. So we can tell the difference between primary amines and secondary amines based on how many NH stretches we see. Of course, tertiary wouldn't have an NH stretch because there's no hydrogen on the nitrogen. We're next going to look at nitriles. A nitrile has one thing that we can identify for a nitrile is the carbon-nitrogen triple bond. That carbon-nitrogen triple bond stretch occurs at about 2220 to about 2260 reciprocal centimeters. Now that's pretty close to what I gave you for the carbon-carbon triple bond. I will not have you distinguish between a carbon-carbon triple bond and a carbon-nitrogen triple bond. I would not do that to you. They are in about the same place. They're pretty close. There's nothing else in that region. Around that 21, 2200, there's nothing else even close. Triple bond, you can pick those out. Let's take a look here at an example. Go to 3000, right below 3000, sp3 CH tracing, that's from these sp3 carbons here, the CH2s. Right above 3000, we got peaks, that's sp2 CH stretching, that's from the phenyl ring. Those are all sp2 carbons, so the CH stretching there, right above 3000. But that nitrile stretch, the carbon triple bond nitrogen stretch, that's this one here at 2247. There's nothing that ever comes in this region except triple bonds. There's nothing even close to it. They really stand out. We can pick out another peak, 1605. That's a carbon-carbon double bond stretch. That's from the phenyl ring. That's those double bonds. And they're a little bit lower than normal because of the resonance of the phenyl ring. Everything else is 1500 and below, not of concern. But a nitrile is easy to pick out. Those triple bonds are easy to pick out. Like I said, I will not have you pick between a nitrile and an alkyne. They come in about the same place. The next one that we have, we're going to look at a Nitro Group. nitro is an NO2 group. This is a nitro group drawn out. It's an O2. Nitro groups show two stretches. They show two different NO stretches. They have an asymmetric NO stretch. And a symmetric NO stretch. So remember I gave you there the earlier symmetric stretching, asymmetric stretching. Okay, so we can see both of them here. The asymmetric NO stretch is about 1500 to 1550 reciprocal centimeters. So right there on the edge of the fingerprint, right before you get to the fingerprint. The symmetric NO stretch is actually in the fingerprint region. It's 1290 to 1360 reciprocal centimeters. Now that is one that I'm going to have you go into the fingerprint region to identify. These two peaks, they're referred to as Nitro Fangs. They're called Nitro Fangs because the two peaks are normally about the same size. And so you've got those two peaks hanging down that's about the same size. They look like a pair of fangs. Like a snake fangs or something. So we call them Nitro Fangs. There's nothing, they're all, like I said, they're always about the same size, maybe just a little bit of difference. Pretty much so the same size. They're always strong peaks. I'll put an S there for strong. Both of them are going to be strong. And they really stand out. It's easy to pick out those Nitro Fangs. Now I went through this one because one of the first labs that we do in Organic 2 is we're going to put a nitro group onto a phenyl ring. And so we will take an IR spectra of our product and you'll have to identify those Nitro Fangs. And so I will remind you of that when we do that lab. But let's take a look here at an example. And like I said, it's not hard, even though we're going into the fingerprint region, it's not hard to find the Nitro Fangs. Okay, if you look at our spectra, I love the 3000. Right above 3000 is SP2 CH stretching. That's from the phenyl ring. The CH is on the phenyl ring. 1600. I guess that's, I can't see if that's a 1609 or 1600. 1609, I guess it is. I can't see.
It's 1609.
Okay, 1609. That's the carbon-carbon double bond. A little bit lower than normal because of resonance. So that's our carbon-carbon double bond. The Nitro Fangs, that's those two right there hanging down. That's our Nitro Fangs. We have the asymmetric NO stretch and the symmetric NO stretch. That's those two right there. So one of them's at 1532. That's the asymmetric. That's in our range that I gave you. And the other one's 1355. That's the Nitro Fangs. So you can see they're pretty easy to pick out. They're two big fangs hanging down there. Not hard to pick those out. Questions? My last slide here is a summary sheet. And I did print one out for you just so you'll have an actual printout. Of course, you do have these on Moodle. But I went ahead and printed one out for you. So here is a summary of all the stuff that we talked about. This is what you need to know for test purposes. This will get you by on test purposes. So as I've mentioned many times today, I love the 3000. I go there first. Slightly below 3000 is SP3 CH stretching. Slightly above 3000 is SP2 CH stretching. Those are easy to pick out. That gives you a lot of information about your molecule. Higher than that, we have SP CH stretching. So that's if you have a hydrogen on an alkyne. You don't always have the hydrogen on the alkyne, but if you do, you'll have the sp CH stretch, and that's about 3,300. In that same region, we also have OH stretching and NH stretching. And I mentioned it's easy to tell the difference in all of those because of the broadness. The CH stretch, the SP CH stretch, is going to be very, very narrow because it can't hydrogen bond. NH stretching will be a little bit broader because of the hydrogen bonding, and OH is much, much broader because it has a much stronger hydrogen bond. So you can, even though they come at the same place, you can tell the difference in all of those. Now, other things that we can pick out, you should be able to pick out the aldehyde CH stretch. That was about somewhere around 2,800. So it's lower than the sp3 CH stretching. It's going to be down here a little bit lower. It's easy to pick that out. We had the OH of the carboxylic acid. It got lowered because of the resonance, and it's extremely broad, very, very broad, because it's got a stronger hydrogen bonding. And again, I called it ugly because it's overlapping with some of these other peaks. So it's not a pretty smooth curve. Here in the 21-2200 region, that was a carbon-carbon triple bond or a carbon-nitrogen triple bond. Again, I will not have you pick between those. It's difficult to tell the difference in those. They're about in the same region there. Carbonyl, about 1650 to about 1850 or so, is our carbonyl stretch. Always very strong, normally the biggest peak in the spectrum, easy to pick out. A little bit below that, we have carbon-carbon double bond stretch. They're weak to medium intensity, so it's easy to tell the difference between these because carbonyl is very strong, be a big peak. Carbon-carbon double bond, even though they're pretty close, carbon-carbon double bond is weak to medium intensity, so they're not going to be very big. And then 1500 and below is fingerprint. This will get you by for test purposes. So if you learn that sheet, you can identify and be able to tell the difference in these spectra. So I'm going to come around and pass out some handouts. I've got some practice problems for you.